Thank you very much, Brian, and thank you very sincerely for inviting me to this. It's a real pleasure to come and talk, and thanks for making the effort to come to this really important meeting. So I'm going to talk to you about biomarkers, and we'll go through some of the things I've been doing and some of my ideas on what some of the underlying causes of this condition might be. So this is the only slide that's got a lot of text on, really, but it's designed to highlight really that the syndrome of MND is really, really very striking. And I'm just going to highlight the bits from this passage here. I'm going to talk to you a little bit about what we understand about the genetics, but as you will all know, that's a very small part of the whole picture. I'm going to talk to you about how it's very striking that people with MND do seem to be quite fit in the main, and that's something I think that's telling us something important. The typical story is of someone with progressive weakness. We often see a foot drop. That's one particular presentation. We might see muscle wasting, but not always. We'll definitely see progressive weakness, and that's an absolute hallmark. And we may see this peculiar pattern of wasting in the hand, where it tends to affect the outer part of the hand more than the inner part. We might see these brisk knee jerks and other reflexes. We'll notice that sensation in the main is generally preserved. And we might see these muscle twitches, which in a normal situation are perfectly physiological. Many of us fasciculate, but in the context of progressive weakness, that's not normal. Now, that is a very characteristic description, and it's actually from 1894. And it tells us that this is not a new condition. It's a condition that's instantly recognizable. There is no doubt at all that that's a diagnosis of MND, just from that description. And that actually underpins all that we do in biomarkers, because it depends what our question is here. And I think our question is, what's the disease activity underlying all of this? Not necessarily, is this MND, but that's one part of it. We can also tell it's 1894 because they've mentioned the name and the occupation of the person, and of course that would never happen in modern times, but it would seem to be acceptable to do that in the journal Brain back in the 1800s. Now, Charcot described this syndrome, this mixed syndrome, which had never been seen before, really, in terms of the description, and it was this upper and lower motor neuron in combination, and really in the whole of neurology would not see that in any other setting. So we get this lower motor neuron involvement causing muscle wasting that may be prominent in some patients. And then you can see those neurons there in green in the middle. And they go out to the arms and legs and the face. And then we have the central motor nerves from the brain. And we see that in the spinal cord in particular. But Charcot never really went near the brain. And that's something that's changed hugely. We now realize that motor neuron disease overlaps with a very, very unusual brain disorder, which in its very severe form is a dementia. And it's not a dementia that's like Alzheimer's. It sometimes gets confused for that, but it is very different. People actually have quite a good social front. They don't really have problems with memory. It's often changes in subtle things to do with personality and sometimes to do with eating. Now, we know that very few, relatively few, maybe 10, 15% in some series, but a relative minority of our patients with motor neuron disease will develop a dementia. And interestingly, if someone hasn't got a dementia at the time that they present to my clinic, I can reassure them that that's not likely to happen. There are more subtle changes that do occur in the brain, but not typically someone developing a dementia. So if it's going to happen, it's usually an early thing. That's a very biologically important thing. For the vast majority of people, they're going to have a much milder sort of syndrome. They might have more difficulty with certain tasks that we might do in research, like the block you can see in the middle there, which is a test of executive function. We ask people to read the words blue, green, yellow, pink, and then we might ask them to quickly shift and read the color of the ink, which is harder. If you try it mentally, it gets difficult. You have to say red, blue, green, purple, and it gets more difficult the more you have to do that. You have to ignore the words. And that kind of activity is not a dementia, of course, if it's difficult, but it's simply giving us a clue that there's more involvement in the brain than is just motor. But you can see the large group on the left. Most people don't have any of those problems. So one of the big breakthroughs really was, how do you define a disease? How do you say this is MND? I don't like the term, there are different types of MND. What I think there are different rates of progression. But how do you define all of one disease? And I think you do that at the moment by looking down a microscope. But we can't safely take a piece of brain or a piece of spinal cord. When we're able to do that in people who've donated tissue, we can see this signature. This brown protein here should be in the nucleus, and it moves out, as you move to the right here, it moves out into the cytoplasm. We shouldn't see that, and that signature is something you will see in nearly every case of MND. So that defines this disease, and we'll see that across all the different types: fast, slow, bulbar onset, limb onset. They all have that protein. As you saw, we'll also see it in half the cases of frontotemporal dementia, and it brings those two together. And so if an alien was looking down at this condition, which I often try to think of it like that really, what would they say? What would they notice about this? And they would say, well, look, yes, it's a very characteristic description, but it also tends to start in one of three areas: speech, arm, or leg. Very strikingly, much rarer, it might start in the breathing area, and occasionally might start in the brain in cognition. But most apparent, it's going to be arm, leg, or face, which happen to be the three major areas represented in your brain in terms of the motor pathways. And it's going to spare your bladder and bowel functions, and it's going to spare the eye movements, and that's a very, very important clue. What's that telling us? And actually, although I won't go into the details of that, it actually is probably more to do with how you're wired together and how your motor system is put together than it is to do with anything special about those nerves. So we're starting to realize that the way you put the wiring together in the motor system of a human makes it vulnerable. Now, a tiny bit more text. It's just that some of the most important things I've learned about this condition have been by reading people who wrote about this in the 1800s and 1900s. And there's Gowers there looking typically happy and laughing as usual. Neurologists weren't very fun to be with in those days. But he was a very serious person, and actually one of the greatest clinical neurologists that's ever been. And he, in his book, 1893, Manual of the Nervous System, showed a very, very important fact that we've kind of reinvented and we think we're very clever in spotting now, but it was well understood that the disease sets its own pace. So for an individual, the disease tends to set its own pace, and that must be an interaction of the condition with that person, and that might be to do with their architecture, how they're put together, various things going on in the cells. And so, yes, it's very difficult when the condition is very rapid. It's hard for us to slow that down, but it's very important for people where it may be slower that they know that it's unlikely and almost never to speed up dramatically. Now, what's the cause of MND is the wrong question, I think, because we've got this motor neuron here in blue. It's got a very, very long axon. If I was a cell body, my foot would be certainly way past Leicester Forest East, back down the M1. This is a very, very long nerve. And so it has a lot of energy requirements. It's going to send a lot of things down the axon here. Very easy to imagine how we might upset that. But bear in mind that anything that we're upsetting in this system doesn't reach its emergence for at least 40, usually 50 or 60 years from birth. So that always has to be borne in mind. So these are not fragile cells, they're highly specialized. But they do need support. They need support from these astrocytes that may overstimulate them. They need support from microglia, inflammatory cells. So there's lots of ways that we might upset the system in the same way of your Ferrari, if you're lucky enough to own one. I don't. My 15-year-old car got me here, though, today. But, you know, even a fine-tuned machine like a Ferrari, there will be subtle ways that you could gradually start to upset that. Perhaps a single grain of sand into one of the cylinder heads over time would start to cause imbalance. So it's not necessarily the system is flawed. It might be that you lose the ability to tolerate change. And fundamentally, although there will be people in the room who develop this condition at a young age, fundamentally this condition is more likely as you get older. And that's true of all sorts of conditions. What that tells me is that there are mechanisms to resist this disease when you're younger that we lose tolerance to, because I think anyone can develop MND, and I think it's about understanding what the mechanisms are to tolerate that and prevent it. Now, we do go to the rare genetic cases because they give us a big clue, and about 5% of our patients will tell us that they have a family history and will be able to identify one of these genes, and the most important one is this chromosome 9, and I say it's important because it's the most common, and it's, along with SOD1, the ones we're hoping to tackle with specific gene therapy. I'm not going to talk too much about that today, but the point is that actually we've started to blur the boundaries, really. I don't ask or regard patients as sporadic or familial anymore, because there are lots of reasons why somebody without a family history might still have a genetic component, even though it's not obviously hereditary. So in fact, we've started to move into a sort of post-familial and sporadic era, really, and we're starting to think of all patients, really, as having a degree of genetic involvement and some having much less simple genetic involvement, but the treatments may well be the same. This is how I think the model works. This is based on a plot done by Ammar Al-Chalabi and others, looking at the log of the age and the log of the incidence. And when you do that, you get this straight line which suggests that there's probably around about 6 different discrete steps that happen throughout a lifetime. So from the moment you're born, 6 things will have to happen and go wrong to develop a rare condition like MND, which is written as ALS here. Now, if you're born with a genetic mutation, probably that means that 4 of those 6 steps are already there from birth. And so it's meaning, as we would see in the family, that it's more likely that someone would get the condition, but not definite. And that's a very, very important aspect of what we're learning about the genetics, is carrying the gene does not always mean you get the condition. And there's likely a whole raft of protective genes out there, which is the new landscape that we need to discover. But I think thinking of this as a much more blurred process, that there are discrete steps. It's just that the genetics may force some of those a bit further. But even in those cases, it's not inevitable that condition occurs. So I think that over a lifetime, you lose tolerance to a lot of things that are going on, different upstream processes, all sorts of different pathways that then converge on a single syndrome that when we see it written down, as my first slide showed, is very, very recognizable. So we have this 3-way sort of split here. We have the lower motor neuron involvement, the upper motor neuron involvement, and the dementia. And actually, for most patients, there's a little bit of both, very little of the frontotemporal dementia, and usually a mixture of lower and upper motor neuron, but for some patients, much more lower motor neuron. If it's very pure, that might be a very slow process. I think terms like PMA are slightly old-fashioned, really. I don't think it's a type of MND. I think it's just simply on the spectrum. And upper motor neuron, PLS, well, PLS is very rare. It's extremely unusual. It's about 3% of our cases. They are a very different group of patients, but I think that we do feel that they have the same fundamental signature within the cells. So the question then is, why is this disease, PLS, so much slower? And so it's enormously valuable being able to study patients with all the range of different types. Even people with pure dementia, frontotemporal dementia, they will have a very slow disease process. Unfortunately, there's a small group, fortunately small, but a small group of people who will have a mixture of very aggressive dementia followed by motor neuron disease, and that is the nastiest of the processes. That is very, very fast. Now, is that because the gate is somehow open to spread this disease between the neurons? And that's what we need to discover. So when I started in research, nobody thought the brain was remotely interested. I got this photo from Chris Shaw from, I think, when he was on Elective. This is a street performer. And really, people thought about MND and said there's nothing to do with the brain. And it was starting here in the muscle, tracking back up occasionally to involve the brain, but not a brain process. And I think if you go away with one message today, it's not that we're suddenly making MND all about dementia. It's simply that this is a brain disorder, like Alzheimer's, like Parkinson's. It's predominantly involving brain motor processes. And that's a very, very important way of looking at it, because it means that the sort of advances we're going to find in other neurodegenerative diseases like Parkinson's and Alzheimer's will have great relevance to MND and vice versa. So there's Nigel Lee, and he asked me if I'd like to study the brain in ALS, MND, and I said, well, he seems like a nice person, but why would anyone want to do that? Because 15 years ago, nobody would have thought that was a good PhD. To be fair, that's my publication, age 7, the brain. The brain is the most important bit of your body. It contains your sight, hearing, smell, your speech. We could not live without a brain. Now, that seems very, what a very gifted child, age 7. Bad handwriting, though, actually. We're not very joined up at 7. But I would just, for balance, say that the next page was the heart, and it started, the heart is the most important bit of your body. And then the lungs are the most important bit of your body. So, but I was very interested in the brain from an early age. And actually, a more important lesson is that Einstein said, if we knew what we were doing, it wouldn't be called research. So actually, sometimes you have to go with the flow, and Nigel Lee knew what he was talking about. So I set to work initially using something called positron emission tomography, and we don't do much of this anymore because the technology is quite difficult to find, although we're trying to get it back in Oxford. And I was drawn to this because this is antimatter imaging. This is, for many of you who know about physics much more than I do in the audience, you can generate positron decay, radioactive positron decay. So antimatter is not something that Scotty would have simply had in the future. This is the real thing, and I got very excited because it felt like I was sort of doing a sort of mini Star Trek, really, and looking after the warp core. But positron emission tomography allows you to do molecular imaging, and it really fired my interest in the brain. And when you do that in motor neuron disease patients with tracers that bind to the inflammation in the cells, you get these amazing signals within the motor pathways, particularly in the motor cortex here. And these two patients, you can see it's just on one side of their brain. And they both had symptoms down the other half of their body, which is what you would expect from the way the brain's wired up. So showing us that there are cells binding very focally within the brain in people with limb problems. This is not a peripheral problem, damaging their muscles per se. It's actually being driven from the brain. And we were also able to demonstrate that their brains were hyperexcitable. And by doing non-invasive stimulation of the brain using a magnet, you could stimulate the pathways. This graph's not so important to know all the details, but it's just, you can see there's a separation between patients and healthy people there. And what that's happening is that the circuits within the brain, the brakes that are normally applying to the brain when you stimulate it, are not there in MND. Somebody's taken the brakes, the padding away, and then made the brain very excitable. Now, whether that's the cause, probably not, but it's a consequence and it's a marker. I'm going to skip over that. The interesting thing for me was, this is all very interesting, lots of things we can discover about the brain, but actually what I'm seeing in the clinic is that we're doing all these drug trials and they're not working. And every time we do a trial, we say, well, I'm afraid it hasn't worked, apart from Riluzole. And why is that? Well, the reason is multiple. But one of them is we make a diagnosis very late. Now, many of you in the room will know that when you first went to see an MND specialist, they said, and I mean someone running a care centre, they said, yes, it's very obviously MND, but maybe it had been a year since you got to that person. And even going to see a non-specialist neurologist, it requires the GP to realise that the problem's neurological. So this is a complex problem delay in diagnosis, and we have the patient here, and I put denial. It may be that, particularly, as I'll show you later, if we do believe that people are very fit, why on earth would you think that there was something terribly wrong with your foot being a bit weak, or your hand being weak, or your speech being a bit slurred, if you've never seen a GP before? Why on earth would you jump to the conclusion in a rare disease that you've got something difficult? So that certainly takes some time, and we can't really get past that other than education. I think this is a big problem, though. The general practitioners, their exposure to neurology may be quite limited, because medical school, you do 4 weeks of neurology out of 3 years. And so if you don't know it's neurological, and if you say they've got a speech problem, they're over 50, maybe it's a stroke, then you're going to go to the wrong clinic. Now, that is neurological, of course, stroke, but you may get sent to ENT. That's not primarily neurological, and often the ENT doctor will say there's nothing wrong. If you've got a weak foot or a hand, you might go to the orthopedic surgeon, who may scan you and say, you've got wear and tear in your spine, we better operate. So there's all sorts of reasons why people might go to the wrong person, and even when they get to a neurologist, it can be difficult. And we're going in reverse order. We're developing tests that I'll show you, which allow the neurologist who's got an unusual case to make the diagnosis more quickly. We're also going and educating the GPs about how to recognize neurological problems, and through the association, of course, educating the population about some of the telltale symptoms, because there are unusual symptoms that should get people pointed quickly towards MND, so that when these drugs arrive, and they will arrive, we'll be able to get them on board early. This is a trial. Here's a trial showing all the participants in the trial and their ALS-FRS score. You might be familiar with this. It's a disability score. It's our gold standard to measure disease activity. There's all the different people in the trial. Some of them are unfortunately got quite aggressive disease and others slower. And you get to the end of the study and you decide who was on the drug and who was on placebo. To make sense of that and to get any signal out of that is extremely difficult. It's too blunt. And we have to do a trial for 18 months and we have to use terrible measures like survival, which is a dreadful thing to have to do. We want to do a study where we measure something and then 3 months later we say, is it working? We don't want to wait for 12 to 18 months when there might be all sorts of other drugs coming out and people want to know if they're on the right trial. So the biomarker value, before I dive into some of the work we've done, is in getting people into studies earlier. And when the drugs come along, as they did for HIV, this was a poster from the 1980s, telling people to take their AZT because better drugs were coming. So I think of Riluzole a bit like that, really. You know, it's not for everyone, and it has a very small effect, and I wish it was bigger. But, you know, it's a small early step, and better drugs are on the way. And we want to get people into studies earlier, and we want to get everyone into a study, not this ridiculous thing where I'm afraid you haven't got enough upper motor neuron signs to get into a trial. That's absolute nonsense. You've still got MND. It can't be just because you don't fulfill some criteria that is based in upper and lower motor neurons. That can't be right that you don't get into a study. I also want to know in a study who's on different trajectories, because if we throw out a drug, but it turns out it was working for a subgroup, that would be a terrible thing. So stratification of patients is very important. And the real prize is the bottom one, efficacy, making a decision much quicker about whether to carry on. So measure something 3 months later, it's not working, let's move on to something else, or 3 months later, actually we've got a signal, let's carry on, or let's double the dose. So I think my contribution has been to tackle this sort of longitudinal, multiple measures study. And it's not easy. It's not easy for the participants. Setting it up from the ethics point of view is actually not too difficult. Patients said, we want to do this. Don't let the ethics committees put unreasonable barriers. But we have to go to ethics committees and say, is it reasonable to take lumbar punctures from patients? Yes, it's not harmful, but it's a lot to ask. Is it reasonable to put people who are disabled into a scanner? Yes, with consent, but we have to have safety measures that they can indicate if they need to come out. So these are challenging studies, but we were able to do multiple blood, spinal fluid, and MRI studies for the first time, and now that's become something of a standard in many, many centres across the world. Does anyone know what this patent is from 1974? Have a guess. MRI, yes, very good. So there's an MRI scanner. Now, it doesn't look quite like that, but actually not that far off. So this was a patent put in for a full-body scanner using nuclear magnetic resonance. And when you first did that in MND, you got these rather grainy pictures where you had some hyperintensity in the motor tracts, but it really wasn't looking as though it would do much. Now, there's been a complete revolution, and it's been led really by non-clinicians. So Irene Tracy, who's our head of department, and Heidi Johansson-Berg, both non-clinical people. Steve Smith and Tim Behrens are computational scientists, extremely clever people who aren't doctors. They don't understand the nuance of ALS or neurodegeneration, but they're very interested in brain disorders. They're very interested in ways that we can pull apart the brain to understand the damage. And I can go to them and say, can you help me show the disease activity? And they can say, yes, we can look at damage on a structural level, and we can look at damage on a functional level, the torque between the cells, how the engine is running, how it sounds, and we can take it apart and see what the components of the engine, how they're damaged. Now, when you do that in MND, you get this signature here through this bridge, the corpus callosum of the brain and the motor tracts. And these pictures here are from 50 years before, and they were drawn from donated tissue by Marion Smith in 1960, long before scanning, and she's drawn in the areas that she noticed that were damaged. And they are exactly what we now see in a living person when we put them in the scanner. So we can now do pathology studies in a live person, and then we can give them a drug, and we can say, is that getting better? We've got certain areas of the brain that we think are particularly hotspots and tell us particularly about someone's trajectory. This area is very, very hot spot of the motor tract descending through the brain, and we think that's quite a good marker of someone's trajectory. The difficult news is at baseline here, look how much the brain is damaged. Now, yes, that person may have waited a year for symptoms, with symptoms before they got a diagnosis. But it may be 6 months, and actually even in those patients there is a lot of damage before, at the time of first scan. Over time we see more damage in the grey matter. That's the sort of the thinking areas of the brain, and the more control areas is probably a better term, rather than the actual outflow pathways. But it's telling us that there is a lot that has happened before symptoms arise, and that is very difficult news. It's perhaps not surprising. We have enormous reserve. If I took a kidney out of any one of you, nothing would change in your blood tests. We've just dropped 50% of your kidney function, nothing's changed. If you take a lung out, same thing would happen. So why doesn't the brain have 50% reserve? It probably does. It probably has a huge reserve. So a lot of damage has happened, and everything is going to be about trying to push back the diagnosis to get there earlier, because riluzole may have a much more powerful effect if we start it sooner. Now, this is just showing you the sort of future of some of the imaging analysis, and it's something called principal component analysis, very well known to any of you who have a mathematics background. And it's asking a machine to say which are the patients, which are the controls, based on data that you give it. And this is separating the patients in red from the grey controls, just on the basis of data that we feed it from activity in the brain. So we feed it the data from neurons firing in the MRI scanner, and it separates out the patients from controls. And that is definitely, I think, a tool of the future. So I want to talk a little bit about what we can measure in the blood and the spinal fluid, because that's going to be a big change in the clinic. And we can measure the breakdown products of nerves, and they're called axons, and they release neurofilaments, and they're the little building blocks, the sort of Lego blocks of the nerve. Now, when you measure it in the blood, you get high levels in patients, lower levels in healthy controls, but you can see there's a bit of an overlap. This person might be wrongly diagnosed here, and this person might be wrongly diagnosed here. When you look at it in the spinal fluid, it's virtually a complete separation. Now, I think that will improve in the blood test, but it's one of the reasons why we have to develop these things in spinal fluid. It's not that we enjoy sticking needles in people's backs, but it's not a dangerous thing to do, but it's a lot to ask, and we wouldn't want to do it if we didn't need to. But it's been enormously valuable to be able to. And what it's shown us is these are the levels of neurofilament over time, and they're quite stable, which fits with what I said about the disease progression. If it's slow, low levels of neurofilament. If it's medium, slightly higher, and if it's fast, higher levels. So the level of neurofilament tells you how active the disease is. So now, in a trial, we can take everyone. We don't have to say, oh, have you got enough upper motor neuron signs, all these sort of ridiculous comments, or how long have you had the condition for, and people get excluded for having a slow disease, which can't be right. But we could put everyone in a trial, and we could say we've got a marker here, neurofilaments, and let's see if we give the drug, if the neurofilament level drops. Because if it does, for everyone, perhaps not so much for some people, it won't drop as much for someone who's already slow. But if it does drop overall, let's carry on, that drug's working. And conversely, if it doesn't drop, we can move on. Now, there are even smaller things going on in the CSF, and there are multiple proteins, thousands and thousands of proteins. And through colleagues, it's not my area of expertise, but through colleagues, we're able to extract those proteins using something called tandem mass spectrometry. This is an amazing piece of kit, just as mysterious and magical in many ways as positron emission tomography and MRI, really, in its own way. When we look back at this period in science, this is full of technology that really only a handful of people in the world know how it works, which is amazing, but also kind of scary. But luckily, I've got people who can show me how it works, and we can get proteins out of the CSF. And when we do that, we've found some new markers. So here's all the proteins. These are the patients here. These are the healthy people. These 3 markers popped out. And no one had ever heard of them before. They're called the chitinases, or chitin is something you find in the exoskeleton of the thing that landed on my head outside. They're not something that you should see in humans. And it turns out that they're doing a different function, and they're probably to do with the immune system. And they're probably a marker of the immune system being mobilized because it knows there's something going on, maybe to clear up cells or to try and support cells. There's some very, very interesting data coming out now that the microglial inflammation immune cells come in and try desperately hard to support the neuron and help it clear that TDP43. So we might have a way to boost that, and we can use these sorts of markers to see if it's working. This is all about linking the very small with the very large. You've probably realized I'm an armchair physicist, and what I think is that the particle physicists down in CERN, they probably, they maybe occasionally go out for dinner with their cosmology colleagues, but they're working in very different areas, and I'm very much a cosmologist, brain scanning, big picture. Here's a picture of all the fibers in your brain here that we've mapped using that technique. But my colleague, Professor Talbot, he's a particle physicist. In fact, he was going to do particle physics. I don't know if Brian knew that. He decided against it when he did medicine instead. So he's working at the very small, but actually the very small is all the things that are going on there are reflected in the very large and vice versa. This is absolutely essential, is to look at both ends. So we're actually trying to look at the really, really small now, and these are tiny little vesicles that are released by cells, and they contain all the information that how the cell's communicating. So it's like tapping into an internet wire under the ocean, really, to see how things are talking to each other. And we think that the disease signature is in there. We think that the cell response, perhaps the cell saying, I'm in trouble, all that response is perhaps going on inside that compartment. And we've worked out a way with colleagues to extract these from people's spinal fluid and to start to look at markers in that. And I think that will be a new area that we'll be reporting on in the very near future. So the Ambrosia project. Well, other rice pudding brands are available. I mustn't advertise. And it's nothing to do with the granulate ambrosia beetle, which releases a fungal product. But no, Ambrosia was the greatest acronym I've ever come up with. I remember being so excited, I emailed Pam Shaw about 3 in the morning. She wasn't awake, and said, Pam, I've come up with a great acronym for this, Ambrosia. So multi-center biomarker resource strategy in ALS. And it was all funded through your efforts, and particularly the Ice Bucket Challenge, which we all remember. So it's a link up between 3 centers, and we're collecting samples routinely in our clinics. And my vision was that everyone wants to contribute, but people can contribute to different levels. Just coming along, giving us a bit of detail about your condition and a blood sample, fabulous, absolutely brilliant. If you want to go, it's a bit like the sort of car wash varieties, actually. If you want to go for the Pro Plus, then yeah, we'll get your CSF as well. And if you want to go for the really super duper, we'll put you in the MRI scanner. But we want everyone to contribute to a level they feel comfortable. And we're going to do that with 1,000 patients. It's quite a lot of infrastructure. There's Liz, my senior postdoc. That's laying out the tray for a single person in clinic, all the different samples that we potentially take, urine, blood, all sorts of things, saliva. And then liquid nitrogen storage we had to get sorted out. And then, of course, we had to find an excuse to hold a tin of rice pudding in front of a college in Oxford. So, drawing slowly to a close, I want to talk to you about something that I do think is relevant to biomarkers, and it's something that's really fired my interest. And one of the nice things about being in Oxford, you can always find people who can help you answer your questions as they come up. I think it's always fascinated me. I do think anyone can get MND. I think that's a really important thing. I think we shouldn't think of this as being born with a set of genetics and that's it. It can happen to anyone. It's just there will be gene drivers which will make it more likely for some people. So who gets this? Well, what I notice in the clinic, yes, not every one of my patients runs marathons, but I see it week after week after week. Generally, people are fit. I see a lot of nurses, I see a lot of builders, I see a lot of people in physical work. Yes, I see people who've never done a day's exercise in their life. It's never 100%, but overwhelmingly, and my colleagues tell me, we see people a bit like Lou Gehrig in many ways. Not professional sportsmen, not Olympic athletes. And the fact that they're not all professional sports people suggests to me that this isn't caused by exercise. I feel very strongly it's not this model of, people like me shouldn't be out on a Sunday, middle-aged men in Lycra, spending silly amounts of money on bicycles, which I don't do. I've got my father's old bike, and it's perfectly fine. And I would not wear Lycra. My wife said that would be it. But I don't think it's running yourself into the ground. I think that this is a marker, really, of certain background risk factors, which may not be modifiable, but they may be a clue to earlier diagnosis. Here's a set of notes from an MND patient and a set of notes from a non-MND patient, not scientific, but again, we just generally, I hear that every week. I've never seen a GP before. I've generally been very well, very fit. Not everyone, of course, but a lot of people. What can we find in occupation? We can find that professional footballers, military service, and agricultural workers have a spike. It's a low-level spike. In the individual professions, they may have their own theory. They may think it's pesticides. They may think it's all sorts of things. The reality is it's a surrogate for fitness. You're not going to be in the military or football or agricultural work if you're unfit. So I don't think that there are individual signals from risk, particular toxins. And we go back to 1893, that report that I showed you there, I can find earlier ones. This is not a modern day disease. This is not caused by something simple in the environment. We know if you have tissue injury, stroke, certain processes in the brain, that can set the scene for this condition, but it's a low-level hit. It's one of those 6 hits, possibly. We know that generally people are fitter cardiovascularly, they have fewer heart attacks in the majority of patients. Of course, I've met lots of patients with MND who have had heart attacks, but overall, more physical activity, less gout. So gout is a really interesting one. Gout seems to be protective for all sorts of neurodegeneration. So that's very interesting, and I'll come back to metabolism in a second. And when we look really early on, we find that people are generally thinner when they were younger. So there are some very important clues, but none of them are going to be, oh yes, you were exposed to that one thing and that's what caused it. It's going to be a sort of person who's more at risk, and that person may turn out to actually be on a number of other levels quite fit. So it's not going to be, I don't think, a sudden moment, it's this unhealthy lifestyle. I don't think we'll have that moment in the same way we've had with Alzheimer's. I think we're going to find actually it might be the opposite, and that's going to be a challenge to work out. Yes, we want to protect you from heart disease, but we also want to protect you from motor system degeneration. Here's a couple of studies that were done last year, not in my group, but very, very important studies showing a sudden change in body weight, maintaining body weight. It changes about 5 to 10 years before the onset. There's a change. Typically loss of weight, but not always, but it's a change. Something changes dramatically in metabolism. And here's the lipid profile of patients who go on to get MND versus those who don't, 20 years before they get MND. So these are GP records from millions of people in the dotted line. And the MND patients, who turn out to be 600 of those, they have a better cholesterol. You may be familiar with high HDL and low LDL. I know I am, because I don't have a good one. But they have a better cholesterol profile than the general population. 20 years before, no one knew that these people were going on to develop MND. So it's not the cause, but it could be a very, very important clue, something to throw into the mix in general practice, some marker of neurodegeneration, perhaps like neurofilaments, perhaps a certain cholesterol profile that we start nationally screening people for at an early age, and when we start to have access to the drugs which are coming. So we put our drugs in here at the moment, soon after diagnosis, and all of this stuff has been building up. The motor neurons have been gradually falling till they get to 50% maybe, and you get symptoms. The cells have been decompensating from birth. We know that. If you do have a form of MND that's to do with a genetic cause, that gene has been abnormal from the moment that fertilization took place. And yet nothing happened, nothing showed for 40, 50, 60 years. So your body tolerates it. And if we know how it tolerates it, we give you more of that. So I don't think of MND as you pull the trigger, it's all over. These are very finely poised, what I would call equilibria within cells, and we only need to push them back a tiny little way just to support the cell a little bit more to get stability at the very least. So we want to put our drugs in earlier. And the way we do that is to study, at the moment, who do I know is more likely to develop MND? It's people who do have a genetic cause. So we want to study people who have those family histories, not just them, but we definitely want to study those people because they've got more chance, their relatives, of developing the condition. But those relatives don't want to know necessarily that they're carrying a gene, and we don't want to test them. We don't recommend testing anyone who doesn't have symptoms. but we like to study them in a way that I don't know their gene result, they don't know their gene result, but someone can put the data together in two groups for me and we can analyze it. And I'll never know who was who. So there's no information that I have they don't, but they could take part in research and we can study people who are gene carriers. And when we do that, here's the patients, the affected ones in red. This is a brain scan. They lay in the scanner for 10 minutes and we looked at the fluctuations, principal component analysis again. Here's the healthy controls in green. Here's the gene carriers in blue. They're not normal. They're not quite the same as the healthy controls. There are changes occurring in the physiology of the brain maybe 10, 20 years before symptoms. And this is the way I think that we're going to move things forward. Now, one of the more sensitive tools is magnetoencephalography, or MEG. Huge hairdryer here, which we can put patients in, actually much easier than MRI. You don't have to lie flat. We can transfer into this chair. It just lowers slightly onto your head. It doesn't go all the way inside. Just sits on the top of the head and records from your brain over 300 points on the skull. And this is someone here on that last, I'll just show you that happening again. This is someone making a decision to move, and it's happening over 1,500 milliseconds. And we can see the brain activity, and then the motor system lights up here, and they make their decision to move. And we can see changes in patients. And these are the sorts of changes we see. I asked the person to move with just one hand. Both sides of the brain light up, because that bridge between the two sides of the brain that I showed you earlier, that corpus callosum, is damaged. So we get this characteristic pattern in patients, but this is what we see in people who have a genetic cause but no symptoms. It's not quite normal. And so actually, and I haven't talked a lot about it today, but with these new drugs that are emerging for those particular types of MND, we've already got some markers and we need them, because we are going to ultimately want to be giving those drugs to people who don't have symptoms. Not probably for a few years. We're going to concentrate on the people who do have symptoms first, but we're going to need a way to measure disease activity. This is the future, a bit more portable though. This is the first MEG scanner. You can get up and wander around, make yourself a cup of coffee and walk around, and it's monitoring your brain. That will miniaturize. I could have shown you a mobile phone from 20 years ago. It was like a brick. That will become standard. We will all wear caps at night, I think in 20 years' time, which will be, from a young age, probably doing all sorts of reading of all sorts of brain activity from a very early age. So this is the way it's going. It's about getting people earlier, before the damage is done. So my last couple of slides now, I just want to highlight the fact that I don't take any of this for granted. I can't do any research without, it's all dependent on patient and their family participation. And I feel that the transaction has to be that care comes first, and that we, by giving the best care we can, we try hard to get it right. We're not infallible, but we try hard to get it right, and getting that right allows then the person to feel much more drawn to take part in research, and then that's a win-win for everyone. So I have a great team of people in the clinic and also a great team of researchers. And a lot of people sort of say, you know, why do you work on MND? Lots of neurologists ask me that, actually. Someone asked me that last night. And, you know, why would you choose to tackle MND? And I sort of, you know, I sat there with Kevin, and I was thinking, you know, why do we tackle diseases like MND? And I'm going to let a former president of the United States, not the current one, tell you why we choose to tackle it. This is a 150 million mile selfie. You can take a 1-ton machine, you can fire it out of the earth, you can make it slow down, you can get it to land, and then you can get it to take a photo of itself and then start trundling around the planet. I think that is absolutely extraordinary. And in a world where that's possible, I honestly and vehemently believe that MND is hard, but it's not that hard. We can crack it. So, why do we choose to?
Not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win.
Thank you.